Okay, so in my opinion, this is where things start to get exciting. We're going to talk about now test-driven development and how we can include this in our software process as we're developing code for this class. Alrighty. So what we're going to see here is this whole process of test-driven development is going to be a cycle of sorts. And you're probably looking at the slide going, what the heck's meant by red, green, refactor you might have an idea about. So we'll go ahead and we'll get into the process with this. I'll show you an example with actual code that you would be able to execute in the Catch2 framework, which again, we'll be using for unit level testing within this course, as well as some rudimentary behavioral testing too. We're not going to get into the framework, the testing framework, Catch2, until one of the lab activities. I believe that will be next, the forthcoming Monday. You'll actually get some hands-on experience with this. And then from that point forward, we'll really expect you to incorporate this process into your, as you're developing, say, solutions to the MP or otherwise within this course. So take careful notes. This is going to be important. It's not that difficult though. So, once you get the hang of it, it'll become more natural. So test-driven development. What we're going to do as we're developing our code is we're going to think about one thing that the code should do, just one thing. So if we're writing a function that perhaps has multiple steps, we're just going to focus on that one step to begin with. We're going to capture our thought in terms of what that one thing the code should do in a test. We'll go ahead and execute our test suite, and we'll see that that test will obviously fail. We haven't wrote any code that would cause it to pass otherwise. So then what we're going to go ahead and do is jump back over to the source code, and we'll write the simplest possible code that allows that test case to pass. Notice we're not looking at doing anything overbearing or overcomplicated. We just want the simplest amount of code that will allow our test case to pass. And then what we're going to do is continue this red-green process. We'll think about another thing that source code should do. We'll capture our thought in a test, execute it. The test case most definitely should fail. If it passed for some reason, something strange is going on, and definitely begin looking into that. And then we write the simplest code that lets us pass the test, and we continue this process. Notice after each red-green stage, there is the refactoring stage, which would allow you to go back through and kind of reorganize things once you're confident that your implementation has been done successfully. The cool thing about this is you already have the test cases. So after refactoring, you can do essentially regression testing and just go ahead and rerun the test to make sure that the code didn't cause you to regress in any sort of way, that those changes didn't introduce any new bugs. And the idea with this whole process is going to be for us to aim for always having working code. And if we go ahead and develop in this stepwise fashion, we should be very confident that, hey, at each kind of green stage, the point up to that point, we should be very confident that our code is working and that it is working correctly. And then if we continue in this cycle, again, the motivation here is to always have working code. So let's go ahead and look at this example. So again, I'm focusing on a unit test of a single function at this point. Our testing will get more elaborate, more sophisticated as the semester progresses, especially after we introduce user-defined types. So write a function, fizzbuzz, with a single integer parameter number that returns the standard library string, fizz if the number is divisible by 3, buzz if that number is divisible by 5, fizz buzz if the number is divisible by both 3 and 5, and then simply the representation, string representation of the number otherwise. So if the number is not divisible by 3 or 5, we would go ahead and just convert the integer parameter to a standard library string and return that to the caller. So test first development. And, if you were going about this on your own, you might consider the number divisible by 3 condition first, number divisible by 5 second, and begin kind of implementing the number divisible by 3 condition first. Ensure that you have that functioning correctly, and then move on to divisible by 5, and then 3 and 5, and then finally this last condition where if the number is not divisible by 3 nor 5, we'd go ahead and return that string representation. I understand that these videos are getting a little longer, so I went ahead and kind of put all of these into one to hopefully expedite our discussion through this. So if you look here, we have test cases number divisible by 3. So this is going to be a single test case. It has the bracket fizz label. We'll be able to, once we introduce catch 2, show that we can execute any of these labels independently of the other test cases. So we could execute our test suite for just the fizz values. We could, or fizz test cases, just the buzz test cases, fizz buzz test cases, or it looks like I have the same name here. So let's call it the number cases. Sorry about that. So if we look here, I have some inputs and output mappings, which I calculated by hand. I walked through the problem to ensure that I got it correct. So fizz buzz of 3, when I invoke this function with the argument of 3, I expect the output to be fizz. And that's what I'm saying here. I'm requiring fizz buzz of 3 to evaluate to fizz. Likewise for 6, likewise for 9. If this test of equality is false, this whole test case will fail because we have some sort of input that did not map to the correct output. And if we have no code, all of these test cases will fail the first time. So similar for buzz, fizz buzz of 5, we're expecting buzz to be returned. Fizz buzz of 10, buzz, 20, buzz. And again, if for some reason our program returns something else, this test case would fail. Then we look at 3 and 5, same thing going on here, as well as for the last case, neither 3 nor 5. So at this point, I can go ahead and run my test cases, and we can see here that everything fails because we have not began to implement our solution yet. So we can see that fizz buzz of 3. Yep, that's when we call fizz buzz with 3. It's not implemented correctly. It's not implemented at all. Same with fizz buzz of 5. In the case of our fizz buzz divisible by 3 and 5, that also failed. And then as well as the neither 3 nor 5 condition. So you might wondering, well, how did I get this to actually compile and run if my function's not implemented? I basically implemented the function in terms of providing a definition that simply returned an empty string so that it would compile and execute. And well, I didn't begin implementing my solution. So in this case, it's failing every time. And you can see here, test cases, this gets your attention. It's in red, big red line, test cases 4, all 4 failed. The assertions, all 4 failed. So when our test cases are initially written, they're obviously going to fail. We then write the minimum amount of code necessary to pass the test. So an astute student might look at this definition and be a little puzzled. That's by design. So let's go ahead and just take it from the specifications without much thought. Okay, if the number is divisible by 3, yeah, let's go ahead and output return fizz. Okay, we could check that off. Divisible by 5, okay, return buzz. 3 or 5, looks fine, though, is it? And then finally, string to number in the condition that we don't have something divisible by 3 nor 5. Now, at this point, I'd go ahead and compile, and I'd execute my test suite. And again, we'll show you precisely how to do this during the lab activity. We'll walk you through all of this, so you'll be able to see how to craft these on your own, how to execute them, how to create them, etc. Okay, so at this point, we've put together this implementation, and we execute it. And notice here that not all of our test cases passed. And the question is why? Well, if we go through here, it looks like we computed the correct value for numbers divisible by 3 by 5. However, in the case that we were expecting a number to be divisible by both 3 and 5, we had an assertion that actually failed. So we had required that FizzBuzz of 15 to evaluate to FizzBuzz. However, it responded, or our function responded with the value of Fizz. This test case then failed, the one that we wrote right here. And notice that the remaining test cases within this test case were not executed. There are ways to get around this if we use topics such as section, but for the simplicity of this introduction, we group them together, and upon the result of FizzBuzz of 15, the test case has instantly failed and it does not need to continue executing the remainder of the cases because it has indeed already knows it failed. So we can go back and we'll revise this. We notice that our initial implementation was incorrect. So we go ahead and we refactor it and we execute our test suite again. And we can see that by checking the conditional as to whether or not the value that is passed to our function is divisible by both 3 and 5 first, we will likely, and we'll rely on our unit test to actually confirm this, return FizzBuzz before going down and saying, okay, well, if it's not 3 and 5, could it possibly be 3 or 5? The problem with the our first version of this code is that, well, if the number was either divisible by 3 or 5, we'd return fizz or buzz. We'd never check the condition. We would never get to the condition where we checked whether or not it was divisible by both. By moving this condition up front, we can see that we indeed checked that one before looking to see whether or not it is divisible by one or the other. So we go ahead, we execute our test suites. Notice at this point, we didn't have to like copy and paste input cases, write a driver with a bunch of different calls to our function, write the return values out to standard output, and then manually go through them and say, okay, are things aligning with my expectations? No. Here we just execute the test suite, all test cases passed, and at this point, we'll get back into this. Okay, well, what's the next step in our program? Write some test cases, write some code, check and see where we are, and continue on the process. So when our test cases are initially written, they'll obviously fail. We will then write the minimum amount of code necessary to pass them. If for some reason, like our first version, the code does not pass the test, we definitely need to go back and revise that, execute the test suite again. And then once we're confident that the code that we've written is correct, that we have working code at that point, we'd continue on this process. So why use test-driven development over conventional debugging? So we kind of introduced that in the informal testing that, you can write statements out to standard out and look at values. You can have print statements and different ways to kind of check whether or not your assumptions were being met at different points in the process. This is, fantastic for debugging, but for testing, it can become a little bit of a nuisance. For instance, with conventional debugging, we'd have to write like 10 lines of code. We'd stop writing, we'd run the program, and then we'd try to figure out, we'd have to provide it some inputs. We'd have to kind of analyze whether or not that was expected output. And if it wasn't, then we break out the debugger and we now have to figure out, well, where potentially could this error be? And depending on how many, say, output statements you have and asserts, it could be dependent on where they are in your application. So it could get very tricky and it might require a lot of tracking down to figure out truly where that logic error perhaps resided. We have to, as I mentioned, insert print statements to print variables while running repeatedly. A little bit easier to do this with the debugger. We can stop in the debugger, tweak set variables to check out how different pathways are executing within, say, a particular block of code. That's fair. But let's say we go through this whole process and we thought we fixed it, but we didn't. Well, we have to go through this whole process again of polluting our code with debugging statements, of tracking the execution, of playing computer, of trying to figure out what's wrong. The great thing about TDD is we write a few lines of code with the test first. We know immediately if it's broken. We can test short pieces of code against our expectations. They'll turn green if they meet them, red otherwise. We have the ability to rerun these tests automatically. So we can easily go jump over, modify our code to hopefully resolve any sort of bugs or failing test cases. And then we just compile the test suite and run it. And we can pick exactly which subset of tests that we'd like to execute. So there's no more of this like running the program 10 times with different input or having to create a driver program that tests the function with 20 combinations of different input and having to then test whether or not the output is meeting our expectations and actually have to manually review. Writing tests before code will take some more time up front, admittedly, but less time overall, okay? The reason being is, yeah, you're writing test cases, which you might not be doing otherwise, but if you hit, some sort of road bump in the way, it's a lot easier to execute your test suite, check whether or not things are passing, kind of deduce where the failures are. I mean, you can implement more code and run previous test cases to ensure that, hey, the new code's not breaking things that I thought were working or that were working up until this point. With conventional debugging, it just becomes a whole process to do this. So we're going to really encourage the use of test-driven development within this course. We're going to require that you submit your test suites for each machine problem, and we will review those to ensure that you are producing adequate test cases. And again, this semester, it's that the bar's been raised a little bit in office hours. We would expect you to be able to pinpoint the code that was added that caused your application to break. We'd expect you to be able to use tools such as test-driven development and unit testing to actually test your code, and then be able to apply, say, GDB as a debugger to actually go through and figure out why those test cases are failing and to resolve them. Now, I understand this is a lot to ask for, at least up front, until you get the hang of it. So, if you're struggling with this or, you're coming to office hours with problems, we're going to do our best to really help introduce these tools to you and ensure that you're using them correctly and satisfactorily for the purpose of this course. Compile frequently would be my other recommendation. Don't try to write a single solution and wait until the end to see whether or not the syntax in your type usage is even correct. It's just, that'll really turn into a time sink to figure out, okay, well, I have to get this compiling first. Where are those errors? Because I don't know what I added to break this. In fact, I don't know what is causing to break. Okay, so that takes a little bit of time. And then once you have the application actually converted into an executable, you now have to go look for runtime and logic errors. And coming up with a methodical way to go about this is really going to be a good investment of your time, because it will significantly reduce the overall time should any sort of errors present.